So to find an equation of a line, we have to actually turn to parametrics and vectors because an equation of a surface, right, where we have an equation with x, y, and z, we can't, that's an equation of a surface. We can't really get a one-dimensional line. I guess it's not. What am I saying? It is three-dimensional, right? So if I think about a line in the y-x plane, we could define it very easily given the slope and then just a point it passes through. And now in the 3D world, right, it gets a little bit harder because once again, you can't really use a equation, like one equation with x, y, and z. You have to turn to parametrics. So here's how you can define a line. We want to use vectors, and we could say that an initial point at a time t equals 0 is given by this position vector r initial, right? And along this line, right, this line is going to be parallel to some vector. This is how we actually define its direction, right? And we can call this vector, let's say for another point right here, r initial, or just r, like at a certain time t. Well, there's going to be this, I guess I can kind of erase this kind of segment here, and I could say, well, hey, there's going to be this, okay, I don't know how you draw two things. I'm not gonna do it. I'm just gonna do it with one hand, or with one marker. We have this vector A, right? This vector A that when you do r initial plus A, you get your r, this new position vector along this line. And the key thing is A is parallel to this line. If it weren't parallel to this line, if it weren't parallel to this line, you can imagine if maybe A was directed this way or this way, then you wouldn't get a point on the line. You get a point somewhere else when you add it to r initial. So how do you get this r as like a function of time in a way? Like how do you get it so that you can express all points on this line, not just one point? Well, we know that a hat, or I keep saying hat, I'm sorry. Well, this a hat, or sorry, I even told myself I say it too much and then I still say it. This a vector is going to be parallel, we can say, to some other vector v, right? And we know that if v and a are parallel, right? If they're truly parallel, what that just means that v, or a, is proportional to v by some scalar. And I can make this scalar called whatever I want, but for parametrics, it can give us an idea if we use it proportional to t, right? So as t gets bigger and bigger and bigger, a gets bigger and bigger and bigger by like proportional, right? So we could say that a is proportional to t, and then I get my final equation, r, and well, not my final, because I'm going to do some other stuff. T times v initial is going to equal my new r, where r is going to be any kind of position vector along this line. So in theory, my line is now traced out by this r position vector. If you imagine this vector like changing by TV, like it's gonna trace, the tip is gonna trace out that line. So hopefully that makes sense. If we know, like let's say v, which is, remember, v is gonna be parallel to this line. Let's say v is defined by a, b, and c, and we could say r initial is gonna be x initial, y initial, and then z initial. So I can rewrite, just using this, I could say, well, hey, r is just going to equal, it's going to equal so each component, right, it's going to equal the, right, when I'm adding vectors, I take the x component here, multiply by time, plus the x component of the initial vector. So a times time plus x initial, b times time plus y initial, and then, sorry, not z, c times time plus z initial. So this is my vector equation of a line. Vector equation, and I can even express this in terms of like a parametrics equation where I can say x is equal to a times time plus x initial. Y is equal to y times time plus y initial. And then z is equal to c time. Did I say y times time? I meant b times time. So yeah, this is now a parametrics equation. In theory, these both, they kind of say the same thing, right? This is just, you can write like a position vector that traces out this line, or you can just express points as parametrics without really needing a vector, like a position vector. If that kind of makes sense, right? Like this is like a specific vector, but this is more like just any general point at a certain time t. So yeah, vectors and parametrics. So just as a quick example, let's write the equation of a line. An equation of a line that is let's say parallel to, I'm just going to use this for parallel to, let's say, this vector. So we'll say I plus 2j minus 3k hat. I gotta add the hat. And crosses, let's say it crosses a point 0, 5, -1. So to get an equation for this line, I just use this kind of formula. I know that its initial, the initial x, y, and z is going to be given by 0, 5, -1. And I know my sort of change in r, right, is, the change in r, right, or the vector that is parallel to the line is given by this. So this vector gives me direction, and this gives me like a reference point. Like, where is this going to initially cross? So I can say, so for a vector equation, I can say r hat is going to equal, so it's going to be, this x component's 1, so 1 times time is just t, so t plus the x initial is just 0, so I just get t here, and then for the next one, I get 2 times t plus 5, and then -3t minus 1. And I can also express this in terms of parametrics, right, using this sort of parametric, I guess, formula, or like, saying that, hey, at t equal, at a time t, this is the coordinates of the point. And lo and behold, if you plug in 0, right, I get x equals 0, y equals 5, z equals -1. And this is not the only equation of the line. There are actually really infinite equations of a line, because I can say my reference, even if I know the reference point is 0, 5, -1, I could be like, okay, well, I know at a certain time, this will also cross 1, 7, -4, right? Because I know that this parallel vector, right, it's 1, 2, -3, so if I add 1, 2, -3, I know it'll also cross a point 2, 7, or 1, 7, -4, and I can set that as like my t equals 0, and then I get a different equation. But when I plug in something like t equals -1 to this new equation, I would still get this point. So there are infinite equations of lines. So just keep that in mind. Another thing we can do, let's actually use the equation from before, is we can actually eliminate the parameter, right? We can express lines in kind of 2 different ways. So we can say, and let me just check my notes, make sure I'm not missing anything. I talked about everything I want to talk about. Yeah, we're doing fine. So what I can do is I can say, well, let's use a line from the last example. So r hat is, let's say it equals t. Let's actually do this, t minus 2, and then we'll do our 2t plus 5, and then what was the last one? -3t minus 1. So I can actually eliminate the parameter. And I guess this eliminating the parameter is more in parametrics, so let's actually just get the parametrics equations out because I think that's a little bit more fitting. But I can eliminate the parameter by saying, well, I know t, right? If I solve for t, I just get x minus 2, right? If I just add 2 on both sides. If I solve for t, I get y minus 5 equals 2t, or y minus 5 over 2 equals t. Whoops. And then I get, so if I add 3t, I get 3t plus z, or, well, what am I doing? If I add 1, I get z plus 1 is an equal negative 3t. And if I divide by negative 3, I can actually like kind of, we could say negative 1 minus z over 3 is going to equal t. So I know, well, these t values are all the same, right? At a certain t value, like at this t value would equal the same as this t value, which would equal the same as this t value. So I can just set them equal. I can say, hey, it should be t's x plus 2. I don't know why I messed that up. I can say, hey, x plus 2 is equal to y minus 5 over 2, which is equal to negative 1 minus z over 3. So this is actually useful because you'll see in a second, it kind of helps us understand the line a little bit better outside of the context of like time. You'll see in a second. I'll show you why this is actually useful. But really quickly, the book talks about it. How do you want to write it? Let's say you want to write the line segment from, let's say, R initial. So let's say you have R initial to R final, or R1. And we want to get an equation for this line segment. Well, what I can do is I can say, hey, well, I know R is going to really equal, wait, I'm going to have to check the book. I know my stuff, guys, I swear, I just kind of forget sometimes. I just want to explain it, properly. So what I know is that, okay, so I know that the R is an equal R initial plus the v vector times time. I think the proper notation is the scalar goes first, so I'll just follow that. Why did I write that like that? Okay. So v, well, v can really just represent the change in like if this is the vector after some time t equals 1, so after 1 second, well, I know that v is just going to equal this difference, right? Because when t is equal to 1, v is just going to equal, wait a second. Yeah, okay, that makes sense. Okay, so this is just going to equal t, this is going to equal r minus r initial. So r1 minus r initial. And then, really, I guess this isn't really r1, but what this is just any r along this segment. So I can get that any r along this segment is going to equal r initial plus tr1 minus tr initial. And then I can factor out an r initial. I can do grouping or whatever I think it's called. I get 1 minus t r initial plus t r1. And this will only apply from 0, or 0 is less than or equal to t to less than or equal to 1, right? Because after t equals 1, it's no longer part of the segment. So this is just a good little thing you can kind of use if you just want a segment, if you not really worried, like for a particle moving along a path, maybe you only care about a certain segment. You can mathematically kind of represent this using an equation. So last thing I want to talk about is how you can kind of use this to figure out if lines are either parallel, intersecting, or skew. So with lines, right, let's get an equation of a line real quick. I'm just going to take this from my notes. And my school teaches this a different way. Like my school, they solve these kind of problems like kind of in an interesting way. And I kind of get how they do it, but I think for explaining, oh my god, I think I'm gonna explain this my way. I think my way makes a little bit more. It's more intuitive, I guess. if you will. But both I think should both should lead to the same result. Z equals 2 minus t. And then, so this is the equation, or the equations that define line 1. And then line 2, its equations are x equals -1 minus plus s. So we're using different, I guess, we're using different, I still don't fully understand this. I believe that changing the variable, right, it's just saying that this is not necessarily the same time as, well, yeah, it could be the same time. I guess it's just another variable to represent the time, right, to differentiate them. Because if these were the same time, then for t equals 0, t equals 0 here would have to equal t equals 0 for here. But that may not be the case, right? This could technically be a line that kind of starts, I guess, at an earlier time. I don't know. This could also represent the scale. So if you understand this better, leave a comment and explain it. But I guess for now you can just think of it as like another variable. So -1 plus s, y equals 4 plus s, and then z is going to equal 1 plus 3s. Okay, so here's how we can determine whether the lines are parallel, skew, or intersecting. So first of all, just to understand what we're asking by that, if you have two lines, if they're parallel, hey, they're parallel. They're never going to intersect, right? And if they do intersect, they're going to intersect, right? Like, there will be some point where the x, y, z is the same on both. But now, there could be a case where they're not necessarily parallel, right? Their vectors may be directed differently. The vector defines their direction. But you can see, if they're initially parallel and I only transform this and rotate this like in one plane, or I guess in the whatever plane, right? If I transform it like this, they're not going to intersect, but they're also skew. So they're not going to intersect, but they're not parallel. So that's what we mean by skew. I just dropped a marker. Let's see how we can go about doing this. Now, one way you can check is you could say, well, okay, you can kind of say, okay, well, at 1 plus 2, so one way, see, like, is there a time where their x, y, and z values are the same? Is there like one specific moment in time, right? So x equals 1 plus 2t. So let's say this is x1, y1, z1, x2, y2, z2. So x1 is going to equal 1 plus 2t. x2 is going to equal -1 plus s. Suppose t is going to equal s, right? Let's say there's a time where they are truly equal. Well, that means that 1 plus 2t is going to equal -1 plus t. And then I get, this is essentially finding a time value where the x's are equal. So if I solve for this, I think I get t is going to equal, and remember it's really equal to s too. I think it's t equals 1. No, it's not. It's not t equals 1. It's t equals -1. Yeah, it's t equals -1. Which negative t values are fine. We're not like, this is not literally time. This is just a variable that helps us, I guess, keep a time frame. So you could have negative time just like in parametrics. But if I test this now, if I say, well, what is y1 equal to? 3 times -1 is equal to -3. And then y2 is going to equal 4 plus -1, which is equal to 3. You could tell, hey, the time value where the x's are equal, it's not when the y's are equal. So these particles do not, or not particles, if you imagine these as particles, like along these paths, they don't collide, right? They don't reach the same spot at the same time. But that could mean the lines still intersect, right? Because if I have a line that's like this, if I have my particle, it's like, moving like this, and I have this kind of trailing behind, they can still intersect, even if it's like a little bit later than when one of the lines reaches that point, if that kind of makes sense, right? It doesn't, I guess one way you just think about it is it doesn't have to be like this. It could more so be like this. So even if they don't reach the same point at the same time, they still intersect. So this is where eliminating the parameter actually helps. And I think you do this in pre-calc. I think it's called non-simultaneous solutions. I'm pretty sure. But what you'd say is like, well, I know that if I eliminate the parameter, I can solve for t. So I get x1, and I'm going to do this. I only actually need x and y. You're going to see in a second. X minus 1 over 2 is going to equal y over 3. I guess we should just do it. Is going to equal z, and I'll just add the 1. z1 over 2. Was this even the right equation? Let me just double check. Oh, it's 2 minus t. That's my fault. So that would end up being 2 minus z over 1. Or I guess it's 2 minus c. And then for x1, it's going to be x2 negative 1 plus, or oh my god, what am I doing? X2 minus 1, no, plus 1 is going to equal y2 minus 4, right? Yeah. And then z2 minus 1 over 3. So there's going to be a point where the x values are equal and the y values are equal. And when the y values are equal, we know that we can essentially solve for y. And we can say that, hey, y1 will equal 3 halves x1 minus 1, right? I just multiply the 3 over. And I know y2 will equal x2 plus 4 plus 1, right? I just add the 4 over. So when y1 is equal to y2, there may be a point, right, when the y's are equal, there may be some x value where the y values are also equal. And I can solve for this x value. So I can say, hey, 3 halves x minus 1 will equal x plus 5. 3 halves x minus 3 halves 5, or yeah, just 3 halves when I distribute, is going to equal x plus 5. X is really 2 over 2x, right, because there's a 1 coefficient. So 3 halves x minus 1 half x is 1 half x. 5 is really 10 halves, so 10 halves plus 3 halves will be 13 halves. 13 halves, and I get x is equal to 13. So I just solved for an x value where the y values are equal. And I can very quickly figure out, well, what time t and what time s is the x going to equal 13. So I could say, hey, 13 is going to equal 1 plus 2t, and I get t is equal to 6. I could say, hey, 13 will also equal negative 1 plus s, and I get s is going to equal 14. So then my last step is just check, hey, what is y1 at t equals 6? What is z1 at t equals 6? And does it equal, and we can just really quickly solve for those. So 6 times 3 is 18. 2 minus 6 is negative 4. And I know that at this x value, the y's are the same. So I know y of 14 is also 18, but you can check that. 14 plus 4 is 18. But the main thing is z. Z at 14, at z at s equals 14, 3 times s, shoot, Jesus, it's not going to be negative 4, I'll tell you that much. It's going to be like 43 or something. Yeah, 43, I think. It's not going to be equal to negative 4. So they're not parallel. I guess I should have checked first. Are they parallel? They're not, because the vector, I guess I'll call it L1, the vector for L. I don't know if that's bad notation, but the vector for that is 2, 3, negative 1. The vector for the second line is, shoot, what is it? It's 1, 1, 3, which you can't, they're not parallel because they're not, there's no like, I can't factor out any of them to get the other vectors, so they're not parallel. So these lines, they're skew. They're not parallel, but they never intersect. So they are skew because there's no value of x or y or whatever where, there's no value of t or s where all three are equal. So hopefully this makes sense to some extent. I don't know. I think lines are pretty cool. But yeah, thank you for watching.